It's always helpful when trying to learn new concepts to look at an example. So we're going to go back to Civil Engineering Systems Analysis by Revell, Whitlatch, and Wright. And we're going to work out an example problem from the chapter Linear Programs with Multiple Objectives. All of these examples, or all these problems in the back of that chapter of this type, have two decision variables. So these are two independent variables, x1 and x2. And the first thing that we need to do is plot the feasible region in this two decision variable space. The first two constraints for that are the positivity constraints, x1 and x2 greater than or equal to 0. So those are terrific. We've already got them plotted out. The next one, x2 greater than or equal to 6, well, that's going to be pretty easy to plot. It looks like this. Less than or equal to 6. So you know we have to be on the bottom or the less than side for x2. Then the constraints get just a little bit more complicated. Let's do negative 6x1 plus 3x2 is less than or equal to 12. First thing we're going to do is find the x1 intercept. So this is the point where x2 equals 0. What does x1 equal? Well, if x2 is 0, x1 is going to be negative 2. That's somewhere around here. Let's find the x2 intercept. So this is x1 is 0 and x2 is going to be 4. And that's somewhere around here. Those two will connect in a straight line. Let's find the intercept with x2 equal to 6. x2, 6. x1 is going to be 1. So that's the line. Negative 6x1 plus 3x2 is less than or equal to 12. And which side is the feasible region going to be on? Well, in the x2 direction, the term for x2 is positive, and we're less than or equal to 12. So in the x2 direction, we've got to be on the less than side or down. But in the x1 direction, the larger x1 gets, the lesser the left-hand side of the equation gets, which satisfies the inequality. So the feasible region will be down and to the right. Terrific. Let's try another one. 3x1 plus 2x2 is less than or equal to 30. Let's see where that one comes up. Try the x2 equals 6 intercept. We get 18 for this term. We need 12 more. So x1 equals 4. What's that going to look like? Then let's try this x1 intercept. x2 equals 0. x1 has to be 10. Bit off our scale. Let me see. Somewhere out there. This is the 3x1 plus 2x2 less than or equal to 30. Because this term is positive and we need to say less than or equal to, we're going to be to the left on the x1 and positive less than or equal to down with x2. Terrific. We can do a few more. 4x1 minus 2x2 less than or equal to 24. When x2 is 0, x1 is 6. And let's get this intercept. When x2 is 6, x1 is 9. Whoa. And this line is the 4x1 minus 2x2 less than or equal to 24. We need to be on the negative side of x1 and the positive side of x2. Let's see, have we got them all from the problem? I think we have. And so now you can see the feasible region is inside these blue hash marks that I'm making now. Anything outside, any combination of x1 and x2 that is outside this area is not a feasible solution. The question remains, which of all of these is the best solution? And for that, we need an objective function, because the objective function is how we measure the merit of each solution. In this problem, the first objective function, z1, equals 9x1 plus 6x2, and the objective is to maximize it. We can begin to systematically test the extreme points, but we're going to use our intuition before we go that far. We want to maximize z1, and so 9x1 is positive in the x1 direction, and 6x2 is positive in the x2 direction. So for z1, we know the maximum is going to be found to the right, and for z1, it's going to be found up and to the right. It might wind up being anywhere against this boundary. So there are two extreme points we want to test. 4, 6, and the intersection of these two lines. The 3x1 plus 2x2 equals 30, and the 4x1 minus 2x2 is less than or equal to 24. We want to find this point where the two of them intersect. What's the value of x1 and x2 that satisfies both of these equations? Let's figure that out by adding the equations up. I hope that looks right to you. x1 is going to be less than or equal to 54 over 7. x2, when we plug 54 over 7 back in, we get another funky looking decimal place. This one works out to be about 7.7. And that could be about right on our chart. And what's the other one going to be? x2, 54 over 7 is 216 over 7 minus 2x2 is going to be 141.48 over 7. There's a lot going on in here. I'm going to leave you to work out which one x2 is at home. And then we're not even done. We have to plug those values into z1 and compare this value 4, 6 and this value, the 54 over 7 and whatever x2 works out to be. Compare these 2 points and see which one of them is the maximum. And we're still not done. We have another objective function. This one is minimize z2 equal to 3x1 minus 2x2. Let's take a look at what that looks like. In the x-axis direction, we know that the Z2 is going to go this way. Z2 is a min. But in the x2 direction, Z2 is going to be a max. In this case, the second objective function is pushing us up and to the left. Whereas in this case, with max, it was pushing us up and to the right. So we expected for here, using our graphical intuition, that we would have to compare this point and this point. But for min Z2 up and to the left, now we're thinking we have to compare this point and that point. Let's take a look. I think we can work these out on an index card. We're going to label each one of these points, each one of the extreme points that goes around our feasible region. We'll call this one A, this one B, this one C, this one D, this one E, and this one F. And let's make a data table. A, B, C, D, E, F. X1, X2. These will be the extreme points. For A, 0, 0. Well, that's easy. Now let's calculate the objective function. For Z1, 0. For Z2, 0. A is a piece of cake. Now let's do B. B was, I wrote this incorrectly. B is x1 equal to 6 and x2 equal to 0. Let's solve for Z1. 6 is 54 and 0. That looks like 54. And Z2, 6 is 18 minus 0, 18. Let's look at C. We haven't solved for C yet. Let's look at D. D was 4, 6. Z1 is 36, and 36 is 72, and for Z2, 4, 6, 0. Let's look at E. E was 1, 6. For Z1, 9 plus 36, 45, and Z2, 3 minus 12, negative 9. Let's look at F. F is 0, 4. For Z2, for Z1, 24, and for Z2, negative 8. C is not a consideration for Z2. So we're going to take a look at the Z2 objective function. We're going to notice a couple of things. The Z2 objective function brings us up and to the left. So the question is whether this extreme point or this extreme point is superior. And at this point, we had a Z2 of -9. At this point, we had a Z2 of -8. This Z2 -9 is the optimum from the Z2 perspective. It's superior to its adjacent extreme points. And so because our objective is to minimize Z2, this extreme point gives us the most negative value, and this would be the Z2 solution. What about Z1? We still have this problem of I haven't done the math on C, and neither have you. So you're going to tell me whether D or C is a superior solution. Let's apply one of the things that we learned about the constraint method. If we were going to take a particular order, and that is we're going to solve for Z2 first, and then we're going to solve for Z1, would we be inclined to improve Z1 by moving from E to D? The answer is no, because once we accept that Z2 equals -9 as a constraint, none of the other solutions from the perspective of Z2 are adequate. They're all dominated, if we were just looking at Z2, by this superior solution. But what if we were to do it the other way around? Z1, and then, which we want to maximize, and then Z2, which we want to minimize. Here's what I think you're going to find. Compare this extreme point and this extreme point. Here we have Z1 equal to 0.72. I think you're going to find the same thing here. There's a reason that I say that. The slope of the Z1 line is determined by the ratio of 9 to 6. The slope of this constraint line, the 3x1 plus 2x2 less than or equal to 30, is determined by the ratio of 3 to 2. And guess what? 9 to 6 is a ratio of 3/2. They're the exact same slope. What that tells me is that along this constraint, we have an objective isoquant of Z star equals 72. D and C are indifferent. That is, they're equivalent in Z1. There's no difference in the value between Z, and you've got to prove this for yourself for C. Solve it all out and let me know. But there's no difference between the value of Z1 at C or at D. So if our strategy, according to the constraint method, would be to solve Z1 first, we could pick any combination of x1 and x2 that lies along this line. Then, when we want to minimize Z2, we can see that a preference will emerge for D over C, because the value of Z2, which we're trying to minimize, will be superior at D compared to C. Let's go over that one more time. If this is our strategy, if we're going to take these objectives in a certain order, Z1 to Z2, and we maximize Z1, we would find that the entire line segment CD meets the maximization criteria. Once we apply the second objective, the Z2 objective, we'll find that the solution, the preferred solution, is found at point D, which has a lesser value of Z2, which we're trying to minimize, than C. Demonstrate that for yourself at home. Figure out what are the coordinates of point C, and what is the value of Z for those coordinates? And put a comment at the bottom of this video. Let me know what you found out.